All right, so we're looking at a graph in this particular problem, and there's different kinds of graphs that we can consider. So this particular example here is called a directed graph. Notice that we have these letter spots, which are basically called vertices, and the things between them are called edges. So a vertex can have a label, edges can have labels as well. A directed graph is only one directional, so A is directed to B and B is directed to C, but notice that B is not directed back to A. We could have a second arrow which points that way for a directed graph, but in this case we don't have that. One way we can represent this is in something called an adjacency matrix. So all of these are the letters of the starting vertices here. These are the ending vertices. And so A is connected to B, which puts a true here, or a 1 if you were doing ones and zeros. So A connected to B, A is connected to B, so that's true. A is also connected to C, so that's true as well. B is not connected to A, so that's false. So this is a way of representing a graph as well that just uses zeros and ones or true and false values. Now if we consider this, which is a bidirectional graph, so both A is connected to B and B is connected to A by default, then basically it does the mirror of this table across the diagonal. So this is now true, this is true, so on. So the reason a graph is useful is that it's a more general purpose data structure which represents basically everything we've done before. So a linked list would be a series of these graphs which are only connected to one other node in order. If I took out this edge and this edge, this would be a linked list, a bidirectional one, which would have like the parent link and the next link. If you had a tree structure, that's a variation on a graph as well. It just has a particular structure. So for example, if B was our root, and we took out this edge and this edge, B would have a child of A, B would have a child of C, C would have E and D as its children. So you can represent all of these other data structures we've been doing in a graph. So if we look at a way of searching through this, there's depth-first search. Depth-first search starts at node A, and let's say we're finishing at node E. So what we're going to do is we're actually going to take a look one link at a time. So A is connected to B, B is connected to C, C is connected to D, and D is connected to E, and we're finished because we've gone from start to finish. Breadth first, you're actually looking at all directions at once. So A is connected to B and C. Then we look at all of those links, B and C, and all the things they're connected to, and we find E. One of the things that's interesting about breadth first search is that you can find the shortest path that way. However, you are doing a less efficient search when you do that. So we have to look at all of the possible links at each step. So oftentimes we use a queue for this, where we basically, we put in all the things it's connected to into a queue. We look at all those things and what they're all connected to. You got to watch out for cycles in your graph or else you'll get an infinite loop.